Welcome back to the video lecture series for Introduction to Data Programming using Scala. In the last video, we introduced the concept of trees. We talked about their formal definition. Now I want to look at how they could be implemented in our Scala code. So, if you remember, our tree is basically a type of graph with some specific rules on it. And the rules are that you can only have one incoming edge. And we talked about the terminology where we have a parent and children. And when we write this, in the case of a general tree, like what's described here, there really aren't any rules for how many children a node can have. We will put some constraints for some particular types of trees, but as a general form, we can have as many as we want. So here we have 3, 2 here, and 1 in each of those. You could have more than this, 3, 4, 5, 100, 200, whatever. So how would we implement that inside of code? It's an interesting thing to question, where have you seen things like this before? And probably in the case of a general tree, the example that just about everyone has seen is a directory structure for a file system, where the root directory, in the case of a Windows machine, it would be C:, and for Linux boxes it's slash. This would be here, and then every file and subdirectory is under it. And in the case of subdirectories, they can have further files and subdirectories under them, and they have kind of a parent-child relationship. So it produces a tree-like structure. So if I wanted to write code for this, we'll go ahead and we'll put it in our ADT. At least start writing something here. So I'm going to make a general tree class. And I guess I can, we're not going to put much functionality here. In particular, we're not going to put enough functionality to actually build one of these. But we can write a little bit of code to kind of illustrate how we would go about doing this. So just like with our linked list, I'm going to go ahead and I'm going to create a class of type node in here. And this class, and of course I gave this a type parameter of A so that I can have some type of data to store inside of here. In fact, so val data is of type A. But what we care about more is how we're going to keep track of all of the other nodes. There are a variable number of nodes. Depending upon how we were interacting with them, we might be adding or removing them. So kind of in the most general sense, the children could be something like a sequence of node. Okay? And so this gives you the ability to store however many you want. Right now this is an immutable sequence. If you needed mutation, we might actually use a mutable buffer in here. So hovering over, okay. Yeah, it's just a general sequence. So this would give us one way of implementing it. Your book also presents the idea that you could structure your tree kind of a little bit differently, so that you have one pointer down to the first child, a reference to the first child, and then you have kind of a linked list. So each node knows about its first child and its next sibling. It turns out that's sufficient to represent any tree that you want. You're basically creating a linked list of children there with a singly linked list with next pointers going through them. But a lot of the times it's easier to do it in the way that we have described here. Now, if we had a tree with this type of representation inside of it, one of the things that we want to be able to do, because this is a collection, it's a container of data, we want to be able to go through all of the elements and do something with them. We'll talk about it as we want to visit them, we want to traverse the tree. And so this leads us to the topic of traversals. How can you go about traversing a tree? There are actually a number of ways you can traverse a tree. One that we're not going to deal with might be the one that many people would do by default. This is called a breadth-first traversal, where you start at the root, and then you go across everything at the next level, and you go across everything at the next level, and then you go across everything at the next level, and complete each level in turn. That's a breadth-first traversal. Oh, it's fairly simple and easy to understand, at least looking at the tree. It's not as simple to code, which is part of why we're not going to worry about it here. When you take a class that actually deals with algorithms, you'll inevitably talk about breadth-first traversals. It's interesting to note that a breadth-first traversal happens to be done with a queue. We're going to look at some different types of what are called depth-first traversals. And in a depth-first traversal, as the term implies, the traversal starts at the root, and then it goes down as deep as it can, and then it pops back up and goes down again as deep as it can, and then pops back up until there's another path, and then pops back up until there's another path. So in the case of this tree here, if we were to give names to our vertices, so this is A, this is B, this is C. Let's move C back a little bit. D. E. F. G. Put G on the other side here. And H. Okay. So I have labeled these in the order that you would get from a breadth-first traversal. Breadth-first traversal would go A, B, C, D, E, F, G, H. When we talk about a depth-first traversal, there are actually multiple types of depth-first traversals, and what distinguishes them is whether you visit a node, whether you deal with it, whatever the visitation might be. So the visitation could just be simply printing it, it could be processing it in some way, doing whatever it is with it. Whether you visit the node before or after you visit its children. So if you visit it before, it's what's called a pre-order traversal, and if you visit it after, it's what's called a post-order traversal. So let's take this tree. In a pre-order traversal, we start at the root, and because we visit the node before its children, we would visit A. So if we come down here and we say, what order would we get for a pre-order traversal? Well, A is the first thing that we visit, and then it goes down. And we visit B before we would go to any of its children, and then we hit E. Now E has no children, so it pops back up. B only had that one child, and we've done it, so we pop back up, and then we go to the next child, which happens to be C. And once again, we're doing this pre-order, so we visit before we go to the children, and then we go down to F, and then we go to H. We're done with H. We've done all the children of F. We pop back up. C has another child, G, so we go to it. And then we pop up to here, we pop back up to the A, and we have one more node to visit, over there D, and we're done. So that's the pre-order traversal of this tree. You can also choose to visit the nodes after you have visited their children, and that would give you what's called a post-order traversal. And you might be wondering, why the heck do I care? Well, we'll see that there are some uses, some situations where pre-order, post-order, and another traversal we'll talk about in order have different meaning for you, and certain problems prefer one over the other. So in a pre-order traversal, you visit each node before you visit its children. In a post-order traversal, you do the opposite. You visit it after you visit its children. So here, while we start at the root, we don't visit A yet because we can't visit A until we've finished all of its children off. So we go to its first child, and we can't visit B until we have done all of its children. We come to E here, and E has no children, so we're able to visit E. And then we pop back up. At this point, we've visited all of B's children, so we're able to visit B. We pop back up to A. A still has more children we haven't visited, so we go down to C, and then we go down to F, and then we go down to H. We can visit the H, we pop back up, We've hit all of F's children, so we can visit the F. We pop back up. We still aren't done with everything under C, so we go down here to the G. We pop back up. Now we're done with all of C's children. We pop back up. Then we go to the D, and we finish off with the A. When you're doing traversals like this and you have to figure out what order things are in, I like to point out that there's a simple sanity check. In a pre-order traversal, every node comes before its children, and since everything else is a child of the root, your root better be first. Okay. Similarly, in a post-order traversal, because a node is visited after all of its children, the root has to be last. If you do one of these traversals and you don't have those properties, you've done it wrong. So there's a simple sanity check for what these traversals will look like. So this kind of explains the basic traversals. The other traversal, the in-order traversal, would be in between the children. I don't personally find that to be as well defined when you have more than 2 children. So we'll revisit this when we talk about a particular form of tree that only has 2 children. So if you have 2 or fewer, I guess I'd be happy with an in-order traversal. We'll come back in the next video and we'll look at how we could write these into code, as well as how we might write some functions that calculate other values that are associated with trees using the beginning of the code for